I'm looking today at sustainable water. In today's class, first of all, we're going to define what sustainable water actually means. We're then going to identify the factors that might lead to not having enough water and analyse which are the largest risks. Then we're going to develop and evaluate potential water solutions to a potential water crisis. Okay, well, first of all, one of the things we might want to think about is, well, what makes water different from other resources? There are a few things compared to other resources we've talked about that makes water very, very different. First up, water is used for absolutely everything. When we think about water use, the first thing we might immediately pop into our head is water for drinking or water for what they call domestic use, so washing, cleaning, and things like that. But in actual fact, water is a critical part of the production of pretty much everything. So yes, we do use it for drinking, there's no two ways about it. But also an awful lot of manufacture. So for example, the clothes that you are wearing, if your clothes are cotton, then the production of that cotton is an agricultural industry. That requires an awful lot of water to keep it going. In addition, the production line uses machinery. That also requires water in its production and also in its operation. And then everything about the way that supply chains work depends on water. Some of the things we might not immediately think about is things like cars. The production of a car requires an awful lot of water. This is because moving things around, generating electricity, all the different components are very, very water hungry. One of the biggest things that actually uses up water is the production of food, and especially meats. So we might not think about it straight away, but to produce 1 kilo of beef for a burger requires using, in some cases, hundreds of kilos of water in order to sustain the cow, produce the food for that cow, and build up the entire infrastructure that's needed in order to supply that cow. But it's not just meat. The production of cereals and various other crops requires enormous amounts of water for irrigation, especially out here in the Intermountain West. So as a result, even the production of grain and things like that requires an awful lot of water as well. Electricity, an awful lot of the electricity we use out here is generated from hydroelectricity. This is electricity generated from dams such as the Hoover Dam. As a result, there's water required in actually the production of electricity that we use domestically and in our industries. And all other foods, we touched on cereals and things like that. But the production of the cereal itself and also the production of the milk that you put on that cereal also requires large amounts of water. So unlike many other things, water is used for absolutely everything. Also, the vast majority of the water that's present on the planet at any one time isn't actually available to us to use in the way that we actually like to employ it. So for example, at any given time, 97%, so this circle here represents all the water on the planet. At any one time, 97% of that water is in oceans and salt lakes. So if we're using it for irrigation or domestic purposes, drinking, cleaning, washing, etc., salt water is absolutely useless. If you were to try and water your fields with seawater, it would kill all the crops straight away. In the same way that if you would start trying to drink salt water, that wouldn't do you any good at all either. So the vast majority of water on Earth at any one time is salt water. Fresh water accounts for just 3%, this little sliver here. And of that 3%, the vast majority of the fresh water at any one time, more than 3/4, is actually ice. So the vast majority of fresh water on the planet at any one time is tied up in polar ice caps, glaciers, or in the snow in the mountains like we have around here. Of what's left, well, water vapor constitutes less than 0.5%. Deep groundwater, so deep water aquifers, constitutes 11%. Shallow groundwater constitutes 12%. And the lakes and rivers that we might immediately think of when we think of water only counts for 0.34% of the 3% that is available as fresh water. So the vast amount of water on the planet at any one time is actually unavailable for the uses that we might want to use it for. One of the things that's worth touching on straight away is that we are in something of a water crisis globally, because we're already feeling the effects of this in terms of droughts, but in the future climate change is going to lead to more droughts in more places. On this map here, this is looking at the predicted conditions from 2030 to 2039. On this map, the sort of lilac colours, lilac-y purple, these show the percentage drop compared to where we are today. Blue shows a percentage increase. And you'll see pretty much for pretty much all of the USA, we're expecting a drop of somewhere between 4% in overall change compared to where we are now. The very, very few places on Earth which are predicted to get wetter, which is this section of Africa is predicted to get an awful lot wetter. They're actually panicking because they're going to get floods and landslides and all that sort of fun things. This region of India and Papua New Guinea. However, right across the Mediterranean regions of the planet, we're expecting increases in drought overall. Even today, water is actually a problem in many places. So I've put this circle up here to highlight. This is the Intermountain West, and specifically targeted on where we are. We are in a condition of sort of extended drought. We're getting an awful lot less precipitation than we do normally, or have done historically, and that precipitation is now distributed differently because we're moving from a snow-dominated landscape to a rain on snow-dominated landscape we talked about before. That means the precipitation that does fall as snow in the winter is melting an awful lot quicker, and so we're running out of water towards the end of summers. One of the biggest examples of the actual water crisis is the Colorado River. If anyone's been down to Moab, a place like that, then you've actually probably driven across the Colorado River. You can float down sections of the Colorado. It's a really, really large river that goes right through a large section of the western United States. The Colorado River has changed markedly. So, for example, if we look at this map over here on the bottom right, the Colorado River used to enter into the Gulf of California. So it would flow down, it comes down through Arizona, comes down along here, enters into Mexico, and this section here is then known as the Colorado River Delta. So historically, the Colorado River used to run right through the US, touch into Mexico, and then enter the Gulf of California through the Colorado River Delta. That Colorado River Delta does not exist anymore. Very little of the Colorado water ever makes it to the ocean. Most years, none does at all. If you visit nowadays what used to be the Colorado Delta, this is what it looks like, a gigantic, flat, dead salt pan. This is a boat that at one point was used in the Colorado River Delta. That has obviously not been in the water for quite some time. And this person, you can see how far they've had to travel to get to even anywhere near this, because look at the amount of camping gear and stuff like that. He's brought his paddles, but I think that is somewhat optimistic, to be honest. And if we look at it, it's not just isolated here in the West, but some of the most dramatic examples exist in other parts of the sea, in other parts of the world. So, for example, now we're going to focus on a place called the Aral Sea in Kazakhstan. You'll notice that this place, actually, if you look at its condition in terms of water arriving in terms of drought isn't that different to what it's been historically. It's only somewhere between equal to where it has been to maybe a drop 0.5% or up 0.5%. The issue with this region of Kazakhstan has been diversions. And what that's meant is the almost disappearance of the Aral Sea in Kazakhstan. The Aral Sea is a large inland sea. This is what it looked like in 1989. This is what it looked like less than 20 years later, 19 years later. It is now a massive, dead, flat salt pan. The reason for this is not due to changes in the amount of water arriving. It's due to changes in what happens to that water after it's there. Specifically, diversions. An awful lot of water in that part of Central Asia is now diverted away, and so it doesn't ever make it to the Aral Sea because it's being used in irrigation and agriculture and things like that. So we have to start thinking, what are the factors leading to a water crisis? We touched on two ideas, which is changes in the amount of water arriving, but also what happens to that water afterwards. Globally, the biggest issue has been, to be honest, us. So if we look on the x-axis here, we have changes in time going from the entirety of the 20th century. On this y-axis, we're going to have two different metrics. We're going to have human population and also water use. On this y-axis, we're going to have irrigated area in terms of millions of hectares. So you can see during the 20th century, human population increased an awful lot. Within 1 century, we went from 1.5 billion people all the way up to about 6 billion people. So our population has increased by 6 times in the space of 1 century, nearly 6 times in the space of 1 century. The also then looked like what has happened to the water. So the water use has almost kept pace with the population. It's actually tailed off a little bit more now. This is because we're now moving globally to a far more urbanized population, fewer people relying on agriculture. But generally, water use has kept pace with the increase in human population. In addition to the water use, look at the irrigated area of the planet. It's increased almost exactly as human population has. So everything else that we talk about diversions, we talk about change in the amount of water arriving, we talk about changes in rainfall. All of that is a problem, but the biggest problem is actually the fact there's just so many more people. When we're talking about water and water conservation, we might have this idea of sustainable water. Before we start, it's really worth thinking about, well, what is sustainable water? Well, sustainable water is the use of water that supports the ability of human society to endure and flourish into the indefinite future without undermining the integrity of the hydrological cycle or the ecological systems that depend on it. What that basically means is similar to our earlier sustainability definition of it allows us to do what we need to do today in a way that doesn't prevent our ability to do it in the future or decimate ecosystems. So when we think about sustainable water, one of the places we really want to start about is we have to learn about what we call hydrographs. And hydrographs, like this one shown here, are basically a record of the amount of water flowing down a river across a year. So in this particular hydrograph, we're starting in October 2005 and we're eventually ending back here in October 2006. So this is the amount of water flowing down the Logan River above State Dam at any day across the entire year. And the blue line is the mean daily discharge. So all over the US, the USGS, the United States Geological Survey, has implanted or has placed these sort of discharge measuring machines inside rivers all across the country. And so you can actually go online and see these for yourself live, and you can see what the historic flows have been. What we can see here, this is a standard normal hydrograph. So we can see the amount of water in cubic feet per second. Down in October, stays very low. All the way through the falls, pretty low. We get this big sort of drop down in January. This is the reason there's very little flow at this point is probably because the river actually froze. Then the river, when it heats up a little bit, starts to thaw. Then when we get the beginnings of spring, this is the point at which snow is starting to melt. And so as a result, the amount of water going down the river is not based entirely on the amount of rain that's falling on that day, but it's based on the amount of snow that is melting that day. And so what we see is standard snow-dominated landscape. Spring kicks in. As we get the big snow melt in this section, that's when we get the most amount of water suddenly running down. The highest flow we see is in mid-May. This is what we call peak spring runoff. And then this is the maximum amount of snow that's melted. We then see a decay in the amount of flow coming through. This is because we're running out of snow in the mountains until we eventually get back down here. And this is what we call a base flow. So there, you can see it's about the same as that. That's what's known as a base flow. That's the amount of water that just goes through it naturally, either spring-fed and stuff like that, without the big addition of snowmelt. And so from these hydrographs, we can then start to think about the idea of the water budget. So the water budget basically works in this very, very simple idea in that if we want to know the amount of water storage, which is the amount of water that can be stored on the landscape, either in dams, rivers, and lakes, we look at the input of water. That's what falls entirely over the course of the year in terms of precipitation. Whether that precipitation is snow or rain or sleet doesn't matter. It's just the amount of water that's coming in. Then we minus the outflow, which is the amount of water that is seen coming out or that we can use. And the difference between those is storage. And as I said, that storage can be in terms of snow, it can be in terms of water in dams, and it can be in terms of what's sitting in lakes. So this bucket illustration is what people often use. So here we have precipitation. So precipitation is the amount of rain and snow falling. That precipitation goes into the bucket, and then we can draw water out of the bucket through this spigot. Incidentally, spigot is possibly my favourite word in the entire English language. It's wonderful. Just take 10 seconds to say spigot to yourself. Isn't it wonderful? The more water that we draw out of this spigot means there's less available here in storage. So here we've got a load of water coming in. We've got a little bit of water coming out. And so as a result, we've got our bucket level is quite high because we're storing a lot. If instead we draw out a lot of water, so we increase the outflow, we've got the same amount of input, but now we have increased outflow. The amount of water stored in the bucket is considerably lower. This is the basic water budget. You take the amount of water coming in, the amount of water coming out, and that then tells you your storage. So if we look at the water budget spatially across the United States, this map here determines indicates the amount of water coming in. And the way that it's doing that is available precipitation. This is actually predicted precipitation for the year 2050, but you can actually go onto Prism or BioClim and get these data for the current state of the world now. And what we see is we've got the available precipitation in terms of inches per year. First thing that we notice is, well, the sort of dark blue, the navy blue, is the really high area. The highest amount of precipitation in the US is in the Pacific Northwest, this section of Idaho and Montana, the Northeast, and also the peaks of the Appalachian Mountains. Then we have this sort of grade. If we work from east-west, we see that we've got the Appalachians. Then as we move across the Midwest, we get decreasing amounts of precipitation. When we get into the true sort of like hardcore Midwest, very little precipitation at all. Some sections of the Intermountain West and the Rockies get a little bit more precipitation. See this part of Wyoming, this section of Colorado gets high precipitation. In Utah, we've got a big gradient. We get very low rainfall in the south. Up here in sort of Logan and out to the high Uintas, we get a bit more, but still considerably less than the Pacific Northwest. And places like New Mexico, Arizona, relatively low precipitation the whole time. Then if we look at, okay, that's the water going in, but now let's have a look at the water going out. So this is the areas with the biggest total freshwater withdrawal. And what we mean by withdrawal is water being taken out of natural ecosystems and used for agriculture, hydroelectricity, municipal water use. And what we see is when we look at water out, it doesn't quite line up with where the water's coming in. So if you remember, most of the water was coming in down the Pacific Northwest, the Northeast, and that section of Appalachia. But if you look where the most amount of water is being drawn out, first of all, the Central Valley of California. This is the big agricultural area. This is John Steinbeck, grapes of wrath kind of land. That's where an awful lot of water is diverted and taken out and used for agriculture. In addition, we have water being drawn out for agriculture in this part of Utah and Idaho. There is a lot actually used in Appalachia. There's an awful lot on the eastern seaboard of the US being used for municipal water use, and this is very high population densities. And also Florida uses an awful lot of water as well. But it doesn't quite add up. If we therefore measure this by looking at the amount of water coming in divided by the amount of water coming out, what that does is it gives us a percentage of water withdrawal compared to available precipitation. Now with this percentage you might immediately think, well, for any one place the maximum amount of water they can withdraw is surely 100%. You can't withdraw more than 100% of something. But that's not strictly true because, remember, water moves around on the landscape. So even if not very much water is falling where you are, you can withdraw more because you can move water around the landscape through rivers or even artificial pipelines. And what we see when we look at total water withdrawal compared to available precipitation, there are lots of areas that are pulling out more than 500% of the water that falls as available precipitation. What this means is, on this map, any area that is this brown colour, they are withdrawing more than 5 times the amount of water that is landing in that area as rainfall. We can see straight away the big withdrawals are this huge section of Texas, New Mexico and Colorado. Also this section of southern Arizona, this is a big agricultural area. Some parts of the Central Valley. Southern part of Nevada, guess what this is for? That's the Bellagio fountains in Las Vegas. And also these regions of southern Idaho. But these are the areas that are in essentially enormous amounts of water debt. One of the things that's difficult about water is that we have to try and predict what's going to happen in the future. And unlike predicting change in temperature, predicting changes in water is quite hard. This is summed up by the old sports player Yogi Berra, who said it's tough to make predictions, especially about the future. If we have a look at what's going on here actually in Cache County, so Cache County has water coming in and water getting used up and municipal water supplies. So we'll start up here. So we've got the average annual river flows in Cache County. So we have 3 major rivers that flow into Cache County. Those are the Logan River, which annually brings in 134,000 cubic feet. Then we've got the Blacksmith Fork, which brings in 70, and the Little Bear River, which brings in 69,000, giving us a total of 273,000 units available. However, this data is originally from 2015. If we looked at the expected decrease in river flow due to climate change, we're expecting quite a serious percentage decrease, so a proportional decrease by 2020, where we are now. The actual decrease we observed is actually greater than that. By 2050, we're predicting that decrease to be even larger, so we're losing about 16% of our water, so about 17%. By 2020, we're going to lose about 20% of our 2070, we'll lose about 20% of our water. If we look at where municipal water supplies, we'll see that, well, the Logan City water system uses up an awful lot of water, but places like Hiram also use a lot, and Wellsville's. So in total, we've got an awful lot of water getting used up. However, we're expecting an increase in the population, and so as we increase that population, the water demand is going to increase with it. So if we start with the base data, this was when if we go back to the year 2000, the population that relied on the Logan City water system was about 42,000 people. Those 42,000 people demanded this much actual water. If we look by the time we get to 2020, the Logan City water system is now trying to serve nearly 60,000 people, and the water demand has increased by about 50%. If we look into the future, the Logan City water system, we're expected to have nearly 90,000 people, and the water demand is going to have more than doubled compared to what it was in the year 2000. If we jump right up to 2070, we'll see that the population has increased by nearly 3 times what it was in the year 2000, and the water demand has also increased by nearly 3 times. What that means is, as we look into the future, and this same pattern is repeated through the Logan Water City system, Providence, Smithfield, North Logan, Hiram, Nibley, Hyde Park, Wellsville, Richmond, Lewisham and all the cities, means that if we look at the county totals, by the time we go from the year 2000, we've gone from 91,000 people up to 270,000 plus. This has been associated with a tripling in the water demand compared to what it was in the year 2000. Okay, and this is just for basically our provincial, culinary water. We've also got to put agriculture on top of it. Interestingly, agricultural water is predicted to go down as Cache County transforms more from an agricultural producing landscape into a more urbanized setting. What this means is, even though with climate change we're expected to receive less water coming into the county, the amount that we want to use is going to be going up by an awful lot. If we take a city like Smithfield and we look at what's going to happen between now and in the future, this is Smithfield for a graph of both municipal water demands and source capacity between the year 2000 and 2070. So this is the amount of water that gets supplied to Smithfield through the rivers and rain. This is Smithfield's demand. You can see that, okay, demand outstripped supply about 15 years ago. Water in has been less than water out in Smithfield since about 2005, and it's only going to get worse. What that means is there's actually now been a very large group of people working out of my department, the Department of Watershed Sciences, looking at preserving Utah's water resources. This is a project known as the iUtah project, and it is innovative urban transitions and arid region hydro sustainability. The project is looking at changing the infrastructure that we have here on the ground in Utah generally to make sure our water is better used. It's also to look at what the water demands are of people. Those are changing through time as we're moving away from agriculture in many places and towards a more urbanized society. And also looking at changes in the way water is moved around the landscape. Those of you that have been here in Logan for a few years might even have noticed that historically, say about 3 to 4 years ago, when we would move agricultural water around the Logan area, we would often use the roads themselves. It's not unheard of if you go down 400 at the right time when they're doing irrigation supply, you would actually see irrigation water to be used for farming moving down the sides of the road in the road gutters, and then that's how they would move the water around the landscape. As you can imagine, any water that's gone over a road is now in very, very poor quality. It's picked up road grease, it's picked up bits of petrol, it's picked up bits of rubber from cars, and all sorts of things. As a result, that water can't really be used for an awful lot of things after it's been passed down a road. What they've now started to do is not only build ditches, but also build buried pipes. So now an awful lot of the water does not go down the road, doesn't go down open ditches, but it actually goes through sealed pipes. What that means is less water evaporates and also less pollutants can get in. And that was all part of the iUtah project. One thing that is really worth thinking about is the relationship between sustainable water, water availability and water demand, and biodiversity. Humans, when they are short of water, will do anything to get hold of it. We'll divert water, we'll move it around the landscape, we'll put dams in, we'll put pipelines between one watershed and another. And what that means is that water can often be taken away from the ecosystems that it was previously supporting. These two maps here kind of illustrate that quite well. So on the top, we've got the incident human water security threat. A low value means that people in that area are pretty confident they've got enough water, there's no real drought conditions, everyone is okay to just tick along and carry on with their daily business. As this increases, it moves from blue to red. That means that people are nervous about the amount of water that is available on the landscape. They're having to increase and carry out an awful lot of water diversions. They're having to move water around, or they're having to draw down subterranean aquifers, more than is sustainable. On this graph at the bottom, we have incident biodiversity threat. A blue value means that the biodiversity in this area is generally fine. There are no massive pressures on it. It's not got a high abundance of endangered species. Red means the biodiversity in that area is heavily under threat. It's heavily negatively impacted and it's generally considered at risk. What we see when we first look at these maps is areas where there's high water security threat, there's also high threats to biodiversity. So, for example, pretty much all of Europe. For those that know anything about Europe, you know that most of the biodiversity in Europe is in a really sorry state. There's very, very little natural areas, truly natural areas, left anywhere in Europe. The only bit of pristine primary rainforest, or primary forest in Europe exists here, in a little tiny, somewhere around here, a little tiny dot between Germany and Poland. The rest of all the forest, all the ecosystems that we think of as natural in Europe is actually, it's been destroyed and then been allowed to regrow. So generally, biodiversity is pretty threatened here. Oh, same with the water. Then we look at other areas. So some of the most populous parts of the world. This part of China has a huge high water demand. This is where those gigantic dams are being placed in, such as the Three Gorges Dam and things like that. It's where the Yangtze River has been dammed and all those sorts of things. That again, we have a really high biodiversity threat. Same in the other populous region, second most populous region, which is India, the Indian subcontinent. Very, very high water security threat, very high biodiversity threat. In the US, here we've got, it's predominantly the Midwest. And then if we go into South America, this section of the Atlantic rainforest in Brazil, another hotspot. So generally, all over the world, we have this correlation between high incidence of human water security threat and high incidence of biodiversity threat. We can actually map that in one map, but what we're doing here is we've got 4 different colours on a 2x2 axis. So we have biodiversity threat, either being low or high, and we have human water security threat, either being low or high. What we can see generally is we have an awful lot of this red colour. This red colour is when we've got an awful lot of high human water security threat and a high biodiversity threat. So that is seen all through the Indian subcontinent, all through China, going down into Southeast Asia, all across just the very bottom of this Africa and the start of sub-Saharan Africa, then going down the spine of Africa, then these big sections in South America. Where we have this yellow, we have high biodiversity threat, and we've got low human water threat. So that's basically North America, this huge section of Europe, this parts of South America here. So we can actually see we've got an awful lot of yellow and an awful lot of red. What the yellow means, it means that biodiversity is threatened even though water is fine. That probably means there's something else negatively impacting biodiversity other than just water loss. So that might be things like urbanization, conversion to agriculture, but water is not limiting, and other factors such as that. We also have an awful lot of this sort of grey colour. This is an area where the biodiversity is quite happy and the human water is happy. What's really interesting is this brown colour. So this brown colour is when we have low biodiversity threat, which means the biodiversity is doing just fine, but we have high human water security threat. So what this means is these are areas where humans on the landscape are really nervous about the amount of water they have, but the biodiversity is doing okay. See if you can find any of this brown colour on this map. I'll just give you 5 seconds. Did anybody find any? Okay, there's a little bit just down here. So this is an area where, I think it's Mozambique, where humans are really nervous about the amount of water they've got, but biodiversity is doing fine. So in other words, there's a very, very tiny portion of the entire globe where people are nervous about water, but the biodiversity is also okay. What does that tell us? Well, it would suggest to us the fact that there's a tiny area like this, but there's an awfully large area that's this red, means that any time humans are nervous about their water, they will start diverting that water, using that water, taking it away from natural ecosystems, and that negatively impacts natural ecosystems, which in turn impairs a threat to biodiversity. So if we are nervous about our water, then to be honest, natural ecosystems are totally triaged because we're more concerned about getting enough water, even if that's at the expense of natural systems. One of the questions that comes up on this, especially when we look at the Intermountain Wests, is, well, why did people settle the arid Intermountain West if there are lots of drought conditions? Well, John Wesley Powell, one of the first folks to explore this area scientifically, led a scientific explanation down the Colorado River in 1869 and concluded that the climate here was unsuitable to support large populations. So the first person to really have a look down the Colorado River and explore this section of the Intermountain West said, this is not a place to put large populations. And yet we've got cities like Salt Lake City, Phoenix, Arizona, Las Vegas, Nevada, sat in this area where the climate has been determined to be unsuitable. However, Charles Dana Wilbur, a few years later, came up with this wonderful quote, which was, "Godspeed the plough. By this wonderful provision, which is only man's mastery over nature, the clouds are dispensing copious rains. The plough is the instrument which separates civilization from savagery and converts a desert into a farm or garden. To be more concise, rain follows the plough." So this shows you one of the ideas about potentially why this area was colonized. For a long time, people believed that if you plough the land, if you convert land to agriculture, then God will provide the rain in order that your agriculture will be successful. They actually believed that if you till and manage the land, rain will be provided for you. So one of the reasons potentially the West was colonized so heavily was because they thought if we just plough it, God will see what we're doing and provide us the rain to succeed. Initially, bizarrely, that actually happened. So, by sheer happenstance, as people were expanding westward, increased rain followed their westward expansion. This was pure happenstance and chance. It just happened to be that people expanded into the Intermountain West at the same time as there was a periodic increase in rainfall. However, Powell, who'd led the initial expedition, predicted that the land, as is quoted, shall have to expect a speedy return to aridity, in which case a large proportion of the agricultural industries of these now growing up would be destroyed. So what Powell actually predicted was, as people were doing this ploughing and saying rain follows the plough and all this sort of stuff, he was like, well, you guys should just, watch yourselves, frankly, because he suspected that this was not going to be a long-term thing and that soon enough it would return back to aridity. If we actually look at how it was achieved, eventually, we know we do have large population centres in the Intermountain West. It's actually through an awful lot of river management. So a big example of this is the Colorado River. So the Hoover Dam, which is the time's biggest dam in the entire world, was completed in 1836. The Hoover Dam is a massive dam that dams up the Colorado River, drastically changing flows, and allows an awful lot of water to be diverted away from the Colorado River into other places across the West, and that's what's allowed agriculture and cities to thrive. Since the Hoover Dam was actually constructed in the 30s, 57 further dams have been put in place into the Colorado River watershed. These dams allow multiple diversions to different states, including California and Utah. So on this map here, we have, this is the main stem of the Colorado River, running all the way down, and eventually supposing to end up in the Gulf of California. We've also got other rivers coming off the side. So, for example, the Green River, the San Juan, the Little Colorado, all of these flow into the Colorado eventually. But here's the Hoover Dam. Here's the Glen Canyon Dam. And these two dams have ended up generating enormous lakes behind them. So Lake Mead, that sits behind the Hoover Dam, is a totally man-made lake. Lake Mead was just part of the Colorado River until the Hoover Dam went in, and that then allowed an enormous amount of water storage to take place in this area just above the Hoover Dam. Same with the Glen Canyon Dam, that generated Lake Powell. Lake Powell is an artificial lake. Prior to the construction of the Glen Canyon Dam, this was literally just another section of the Colorado River. In addition to these major dams, we have lots and lots of smaller ones all over the place, going right the way up into Wyoming. One of the things that you'll notice about the Colorado River is the number of states it actually flows through. So parts of the Colorado River watershed are in Wyoming, Colorado, Utah, Arizona, New Mexico, California, and Nevada. So this is a huge, huge watershed. And what's interesting about the Colorado River is that not only is it dammed, but the water is diverted. So an awful lot of the water that serves Los Angeles County, one of the biggest population centers in the entire West, which is sort of over here, it's not even on this map, pretty much all of that water that serves LA County is coming out of the Colorado. So as a result, the water that fell into the Colorado is being diverted and dammed, and it's changed the flow of the Colorado dramatically. The biggest way that we look at these flows is the annual flows of the Colorado River in million cubic meters into what was the Colorado Delta between 1905 and 2005. So this up here is the standard Colorado River flow. At this point, the reason it's declining is because this is an awful lot of water diversions taking place. Then, remember, here is 1935. We have this big section here. This was the construction of the Hoover Dam. Then we have this continual decline until by the time we get to sort of 1960, especially the early 60s, absolutely no water at all basically made it into the Colorado River Delta. At this point, that delta ceased to be. It was no longer a river delta. Because it was not making it to the ocean, it can't be classed as a delta, and the Colorado River itself never made it to the sea. During this section in the 70s and 80s, there were large rainfall taking place in the Intermountain West. And we talked about the floods in Salt Lake in 1985 and 86. As a result, some of the water there was so much water in the Colorado River system, some of it was allowed to make it all the way down to the ocean. In the early 90s, it was decided that we should just make sure some gets there. That's happened once more. But generally, no water from the Colorado River makes it to the sea anymore. In addition to changing the amount of water that makes it all the way to the ocean, dams also change the distribution of that water during the course of the year. So, this figure is a little bit hard to interpret, so we're going to go through it slowly. Basically, on the x-axis here, we have time. On this y-axis, we have month within a year. And just like we did on the original hydrograph, we're going from basically July all the way up to October. This is the different years. And on this axis, we have the discharge. This is the amount of water coming out. This particular hydrograph is looking at the Green River in Utah from the years 1929 to 2000, before the Flaming Gorge Dam was completed in 1963, and then onwards. So this line here, this is the dam, this is the completion of the Flaming Gorge Dam in 1963. So prior to this line, there was no dam, and it was basically natural flows. After this line going this way, we now have managed flows that are being impacted by the dam. So what we can see is before the dam went in, we have the standard snow melt dominated system where we have lots and lots and lots of peak flows, hydropeaking, various sort of flows going in during this point of the year. Then later on, when we hit base flows, this is basically when all the snow is melted and things like that, we get an awful lot less flow. When we put the dam in, what we notice is flows never get really so high as they did continuously here every year, but they also don't get so low. But the reason we do this is because this water is being provided as irrigation and agriculture water further downstream. Before the dam went in, the river would get so low during this part of the year that it was unable to support irrigation water. It couldn't provide enough. So what we do by putting the dam in is we reduce flows at this time of the year, we store water, and then we release flows later in the year in order that it can be used for agriculture during the hottest portion of the year, or the driest portion of the year. What that means is a dam can be used to change the way water is distributed through the year, so that rather than having the biggest flows when there's the most amount of rain, and so you don't need water for irrigation, you instead store the water during the periods of high precipitation and then release it later so that much more can actually be used in agriculture. However, the species that live in the Colorado River are not adapted to those changes in flow. And altering the hydrograph, changing the way water is distributed through the year, has impacted native endemic fish. And endemic means fish that are only found in the Colorado Basin. So this is fish like the razorback sucker and things like that. Because what we've done, through this changing of the way water is provisioned, we've altered the flow regime. So in addition to just literally damming the water so fish can't migrate upstream and downstream, we've also changed the timing of the year when large amounts of water are being released, and that affects the spawning habitat of these species. In addition, we've changed what the habitat is actually like. So what we get now is cool, clear water instead of turbid, warm water. So the fish might need different types of water at different times of the year to aid in spawning and migration, and we've altered that, which has negatively impacted fish populations. Okay, that's as far as I wanted to get to today on sustainable water. I'll speak to you soon.